So let's start our journey into the calculus of variations by looking at an actual physical example. So what we have here is a rope in yellow, which sits over the top of a couple of pulleys in blue. Now these pulleys are free to rotate. So let's imagine we grab the rope at this side here and at this side, and we drag the rope down. Then the rope would straighten out along here. Now whenever we let the rope go, the weight of the rope at this side of the pulley would drag it back down into this position. So equally, if we were to grab the rope at this point here and this point here and drag it down, then when we released the rope, the weight of the rope on this side of the pulley would drag it back again to this position. Now we call this position here the equilibrium position, and we're going to look at answering two questions. So one of the questions is, what is the actual shape of this curve? Meaning, can we create a mathematical function that defines the shape of this curve? And secondly, we want to know, why is it that the rope sits in this particular arc? Why not choose some other random arc? Now this isn't a physics course, it is a maths course, but we're going to introduce the ideas of the calculus of variations through this physical example. So we will learn a little bit of physics and we'll learn it as we go along. So I'm going to answer really the second question and just state it, because we don't want to go through all of the physics, we just want to be able to use this as an example. So the reason why the rope sits in this particular arc is that it sits in an arc which will minimise the gravitational potential energy. Now I've just kind of pulled that out of the hat, and I'm asking you to accept that, because we're not going to go through any proofs here of the physics, because we're just going to use this as a mathematical an example. So what we want to understand here is that the rope sits in a particular position such that it minimises a particular quantity. Now the particular quantity that it minimises in this case of the hanging rope is the potential energy. So if I was to move this rope into any other shape, for example if it was to sit straight along here, then the height of the rope will have increased, but the length of the rope will have decreased. Therefore the mass of the rope will have decreased from this point to this point. If I was to have the rope and pull it down into a much lower position, then the heights of the rope would have decreased, but the mass of the rope would have increased because it would have dragged more of the rope over the pulley. So we have this interplay between the mass of the rope and the height of the rope, which is dependent on the shape that the rope sits in, that is the curve that it sits in. And we have said that it sits in a particular shape such that the gravitational potential energy is minimised. So let's look at it in the next slide and we'll see what we mean by the gravitational potential energy. So I've redrawn the rope out here in yellow over the couple of pulleys, and we can see that I've put in the height. So let's say we have a particular height here. So in effect I'm kind of sampling the rope at certain points. So here's a height h1, h2, all the way along to hn. And we have a little segment of rope, and the segment of rope will have a mass m. So we can see that if the rope was sitting in a straight line here, then this length of the segment here would be shorter than the length of the segment here. So this mass here would be less than the mass of this length here. But the height of this part here would be greater than the height of this part here. So you can see that we've got this interplay between the mass and the height. Now I mentioned that it minimises the gravitational potential energy. So let's have a wee look at a heuristic derivation. So don't take this too seriously, it's just a method of getting us started on the physics of the system that the example we're looking at. So let's imagine you had dropped a stone onto your big toe, and what we're going to do is we're going to equate the gravitational potential energy with how much it hurts whenever you drop a stone onto your toe. So if you had a stone of a particular mass and you dropped it onto your toe, it's going to hurt. If you increase the mass, it's going to hurt even more. So really what we're saying is how much it hurt is directly proportional to the mass. So as the mass goes up, the pain goes up. So really what we're going to say then is the potential energy is directly proportional to the mass. As the mass goes up, the potential energy goes up. Now equally we could say that if we were to drop it from a height h, it's going to hurt. If we were to increase the height, then it's going to hurt even more. So you can say that potential energy is directly proportional to the height. Now there's one other thing in play here, and that is that if we were to drop the stone onto your toe in the moon, then it's not going to hurt as much because gravity in the moon is less than gravity on Earth. That is, it accelerates less than it does on Earth. So we can say therefore that the potential energy is also directly proportional to the gravity. As acceleration due to gravity increases, the final velocity that it hits your toe will have increased, therefore it's going to hurt more, so the gravitational potential energy is going up. So you can say that potential energy is directly proportional to the mass, the height and gravity, such that we can say that the gravitational potential energy equals mass times gravity times height. So we are looking to find the gravitational potential energy of this rope here, and we know it's equal to the mass times the gravity times the height. Now the gravity is really a fixed value, okay, because we're on the Earth and it's a fixed value here on the Earth, so we can take the gravity out of this equation. But we know that the mass of each of the elements of the rope, and you can see I've split the rope into these little elements, so the mass of the little elements is going to change dependent on the shape of the rope. So for example, the mass of that element there is less than the mass of that element there. So as the shape of the rope changes, the mass of the elements change. Also, as the shape of the rope changes, the height of the little elements change. Now I've only picked out a certain number of elements here, but what we're going to have to do is we're going to add up all of the elements along the entire length of the rope. So we're going to have to split the rope into an infinite number of small elements of various masses and various heights and add them all back up. So we're really looking at using differential calculus in order to split the rope into an infinite number of straight lines, and then we'll do the algebra on the infinite number of straight lines. And when we've got the algebra in the right format, then we have to add up all of the values for every single length of every single element of the rope. So we're going to have to use integral calculus to add it all back up again. So right now at the moment we could say the potential energy is going to be our M1H1, M2H2, and an infinite number of these all times the gravity. But we'll go and we'll have a look at this actually in the next video, and we'll derive it mathematically. That's all there is for this video. I'll get you on the next video. Goodbye.